Hi, everybody. Thank you very much for inviting me. And I feel a little bit out of place because my background is in computer science, and also just following this amazing talk. It's a pretty hard thing to do, but I'm going to tell you something completely different on very many levels. So first, there is no omics in my talk. And there is only one project that we most recently have done. But this is our attempt at doing something with the very rich phenotype that one can collect in a clinic. So I have no conflicts, but I am sponsored by a lot of the Canadian funding agencies, and I want to make sure to do the attribution before and after to an amazing student who has done the work that I will be presenting, Sana Tanika Boni. She's a master's student jointly with Mike Brudno. So this project started a little bit with a story, and this story is happened about a year ago at SickKids ICU. So a 12-year-old boy had a ski accident, and he was brought by helicopter. He had a femur fracture, and so surgical intervention was necessary. So unfortunately, post-surgery, he got a clot that ultimately traveled from his leg to his heart and caused a cardiac arrest, so which resulted in a severe brain damage, irreversible brain damage. And so this boy was completely healthy, so unlike the previous talk, this is not a heritable disease, and this is something that can happen in ICU, even though there are really highly trained professionals there, and the patients do get the best possible care. Preventing brain damage is really, really hard once a patient had a cardiac arrest. So the best way to prevent this devastating effects of cardiac arrest is actually to prevent the cardiac arrest itself. And I think there's a lot of work being done to actually try to make it happen, right? So there's a lot of data that's being collected on the patients in ICU. The problem is it's too much data, and it's really, really hard to figure out which portions of this data are the right ones and what will actually trigger it, right? The clinician comes in and out of the room, and they have to quickly make a decision, right? So right now there's a lot of data overload, which is not entirely helpful. The good thing is that algorithms and in general can have no problem with processing a lot of complex data simultaneously. That's what they are designed to do. And we can actually use the algorithms to help process the data to give clinicians the right information, or hopefully useful information to parse all of this mess. So I want to step back a little bit, and I do it because there's a lot of attention in the media right now to AI and artificial intelligence, and people are worried about if the killer robots are coming to disrupt our lives, or the jobs will be taken away, or things like that. So I want to maybe settle it down a little bit, because the way that AI is being described and is shown in movies is that it's this kind of super intelligence within the computer that can really solve all of our problems. It doesn't exist. It doesn't exist. We're not close. What does exist, and I think what can be really helpful in a clinic now, is this kind of ability to solve very specific questions given sufficient data. And I think that's a key to the advantages that can be taken out of AI that is being developed now. Machine learning is something that's not mentioned in the literature very much. I don't know why, because that's what's really happening on the ground. And machine learning basically helps this narrow sense AI happen. That's what it is. It's machine learning. And finally, deep learning is one of the types of the methods that I'll be talking about. It's a a type of method in machine learning. So with that, maybe this is the only thing that's useful in my talk, but hopefully this can be useful to you. There are a lot of success stories that are happening already where machine learning is being used in the clinic. So this is a figure from the Science Translational Medicine in 2015 from my colleague at Hopkins, Suchi Saria's group. She actually took the physiological measures and made predictions up to 36 hours in advance of a septic shock, which is another devastating thing that can happen at the hospital. The cool thing about this is that they're actually implementing it right now in the Hopkins system, in the clinics, this predictive tool. And there are many. I'm showing 3 more, but the reality is there are many, many instances where machine learning researchers have been working with the clinicians to take the data, try to understand the data and parse it and build the models to be able to solve it. And most recently, as we were working on our work, there was one that was trying to detect heart failure as well in a hospital setting. So our question was, can machine learning help to prevent cardiac arrest in ICU? The data that we had was the T3 system. Some of you might have heard about it. I think it's used in a couple of places in the world. So this is track and trajectory and trigger data. The patients are hooked up to a lot of monitoring systems, and the data is being collected. So this is multimodal, and it records and visualizes physiological signals for the clinicians to see. So this is kind of below. You see a table of the data that the data set that we worked with, and this is the main signals that we worked with were heart rate, respiratory rate, pulse rate, oxygen saturation, ambulatory blood pressure, and these are. We had the data on a 5-second resolution over 24 hours, so it's a lot of data. On up to 203 subjects, of which 20 last ones were completely left out for testing. So there are a few steps to dealing with this data in a kind of a machine learning setting. We have to pre-process it heavily for it to be actually useful and not to learn the noise in the data. And then we have to build a training set that will actually allow the machine to learn and then test it. So for pre-processing, we did low-pass filtering because there was a lot of noise. Also, there was a lot of missing data. So the sensors, they drop from the patient. And this is, of course, the biggest signal that you see in the data is when it's missing. It looks really dramatic. So that's not what we want to detect. So we have to get rid of this effect. So we used low-pass filtering and imputation. To build the training set, we kind of separated the 2 hours before the cardiac arrest, and we called it the cardiac arrest, the pre-arrest range. So the cardiac arrest also, it's kind of hard to nail precisely. So what we do is our colleagues at ICU, they label the 10-15 minute period where the cardiac arrest is actually happening. So we leave that period alone completely. That range is all called cardiac arrest, anywhere within that time. So then we take the 5 minutes before, and we also leave that out. So this is 2 hours before clearly there was no cardiac arrest, but right before the cardiac arrest onset. And then we look at, maybe I should put some numbers. So we look at, say, 5 hours before the cardiac arrest time, and we consider everything for that patient within the 5 hours before the cardiac arrest as normal signal for that patient. Now, this is normality with respect to cardiac arrest, right? In ICU, obviously something is wrong with them, so they have a lot of different effects in their data, but we consider that normal. So that allows us to maybe get rid of some of the false positives that could easily happen. So we take 2 hour windows in the pre-arrest range, and we take 2 hour windows in the kind of the normal range, what we call normal range. And this is, I'm not sure About the usability of this slide, it's the deep learning models are kind of always represented in this way, but I want to give you a sense, intuition for what they actually do. So the idea is they take the snippets of the signal and they actually translate that into kind of automatic feature selection. So they take moving window over the signal, and all of that information is fed into the algorithm, which then figures out which ones of the snippets are actually useful to the prediction. Okay, so this is this part where it's an automated feature selection, automated sub-signal selection type of thing. And then what it also does is it has this kind of new type of architecture. It's called long short-term memory architecture, where it actually encodes the dependency between the neighboring windows, right? There is a temporal dependency, and it's very, very important. The features themselves in the top part of the model, they are not really tied together. But at some point, we do tie them together so that the temporal dependence actually comes into play. And then at the end, we predict the risk score. So the risk of the cardiac arrest happening within the next 5 minutes in our case. So we actually built a model like that for every signal that we had independently. So we had different types of signal, but that's not the reason why we built them independently. One might think that when you join the signals, it will be much more rich, it will make the model more rich, and maybe the predictions better. But there's so much missing data. So for example, in this particular, this is one patient data, and they didn't have SpO2 and respiratory signals for the period of time that we cared about. And that doesn't mean that our system now should have to impute the whole type of signal for that individual. That's hard to do, and I'm not sure it would actually help us. So what we do is we actually build the system and then build the ensemble model, which says, okay, we have a lot of the heart rate signal over time, and it seems to be a very good predictor, so we have this kind of higher weight to making the prediction. So each one of the outputs of this model, so if you have the signal, then the output of the model is weighed into the risk prediction. If you don't have the signal, it's just dropped. So we take advantage of all the signals, even though they were modeled independently. Okay, so this is validation, this is cross-validation. So we take the training data, and we kind of take a part of the training data and predict on the left out. And the performance is actually this is the positive predictive value. So if you have a cardiac arrest, how likely we are to detect it. And it's kind of on the order of 80%, which is really good, depending on the signal. Some signals are worse. And then we took the 20 samples 20 subjects that we actually had not seen in the data before. And on that 20 subject set, we actually did quite as well as the training set. So this is always a worry. Did we, what's called overfitting to the data, did we just encode what we saw in the training set, or do we actually have a method that can generalize to the patients that it has not seen before? So it looks like this approach actually is generalizing to the patients that it has not seen before. And the ensemble performance seems to perform better than any individual signal for a given patient. So what are we hoping to actually happen with this type of approach in the clinic? We are hoping to have all of the signals, showing all of the signals, but also showing kind of the risk. And this is what the clinician can monitor. So they can also check each individual components, but the system will be predicting the risk as it goes, and then it says, okay, the risk is really high that the cardiac arrest might happen in the next 5 minutes. This, in discussions with the clinicians that we are working with, they say 5 minutes. If we know 5 minutes in advance, it's actually enough to prevent a lot of them. So we really hope that it's actually going to be relevant and, in a clinic at the bedside. So to conclude, the key learnings for us are that for me, I've been in the field of kind of working with omics data and also trying to more recently switch into this phenotype and working with both, is that the health data and the medical data and the omics data is very noisy. and it's very dirty, and there is missing data, and it's not like we are going to collect enough of it and that we'll just put it in a machine and it'll work out. No. We have to be very mindful of what the data represents and what it captures. We have to spend a lot of time pre-processing the data so that we actually have the right signal that we are trying to capture. And in my experience, working very closely with the ICU clinicians, so we actually had bi-weekly meetings where we discussed our results, and it really helped us to narrow down what is the actual question that we can that we should be addressing in the end, right? Because there are many things that the machine can do, but what we want to do is to actually help. So on average, 70 to 75%, it's actually been better, but we would like to, if possible, to move it into shadow trials just to see if it really performs well in a clinic without actually affecting any the clinician's day-to-day actions to see. So in my experience, I think deep learning methods and just machine learning in general can help to make sense of very complex data. And I think working together for computer scientists and clinicians, we can actually do some amazing things. And I want to thank Sana again. This is her thesis work. And I want to bring the attention to the ICU team because I don't think it would have happened without them. And thank you for listening.